Please title these notes Geometric Applications 3 Notes, Area with dy. By the end of this lesson, you should be able to find the area between two curves if you are drawing your rectangles horizontally rather than vertically. So, what we're doing, sometimes we need to draw horizontal rectangles. So that's like this. To find area rather than vertical ones. So the vertical ones are what we were working with last lesson. They're the ones that look like that. We can do this we just need to make sure that we have the same variables for our width and our height. Let's start off with a comparison of vertical versus horizontal rectangles. So over here are the vertical ones. This is what we were doing in the previous lesson. Over here are the horizontal ones. That's what we're doing today. And I'm just going to draw my axes in pencil so that they don't just like overwhelm everything else that I'm drawing. So over here on the vertical side, I'm going to have the function f of x equals 2x, and I want to find the area bounded by that, bounded by the line x equals 1, and bounded by the line y equals -1. So what we've done in the past is we said we're going to be finding this area right here. That purple area. And we're going to draw a nice little sample rectangle here. And I'm just going to tell you that this point up here is the point 1, 2. This point down here is -1/2, -1. And what we saw in the past was that this little width right here was dx because it was infinitely thin in the x direction. And the height was the top function, so that's f of x, minus the bottom, which was -1. Or 2x plus 1. So when we took that and we set that up to be our integral, our starting point for x was right here. Our ending point was right there. So we started with -1/2, ended with 1. Our height was f of x minus -1, or 2x plus 1. And then our width was dx. For the horizontal rectangles, I'm going to start with the same picture, so we still have this, and this, and this. We still have the same area, the same points. However, instead of having a function in terms of f of x, I'm going to have a function in terms of y. So I'm going to call this f of y equals y over 2. Notice the variable is different right here. And I'm going to show you how to convert from here to here a little bit later in the lesson. But we're still finding this area right here. But now, instead of drawing a rectangle up and down, we're going to draw a horizontal rectangle from side to side like this. So what changes here is that now, instead of having a dx width, our width is infinitely small in the y direction. So width is dy instead of dx. To find the height, oh, I should have marked over here that height was the top minus the bottom. Over here, the height is the right minus the left. And think about why that is. If we know that this value right here is 1, let's say this value over here is 1/2 or something like that, then to go from 1/2 to 1, we add 1/2. That's the same as saying 1 minus 1/2. Just like here, the top minus the bottom gave us the distance between. Here, the right minus the left gives us this distance right here. If you do left minus right, it's going to give you the opposite of it. So make sure you're doing it in the correct order. So in this case, the rightmost function is this x equals 1. And then we're going to subtract this left function, which is f of y right here. F of y equals y over 2. So what we're doing is we're doing 1 minus f of y. And that's 1 minus y over 2. Now, instead of our starting point being the x values, when we're doing these rectangles, we're starting off right down here. We have a bunch of different x values as we draw this rectangle, but there's only one y value. It's y equals -1. It's the y value right here. So that's where we start. And then we keep drawing rectangles until we get up to here, where our y value is 2. So when we set up this integral, we're looking at our start number is -1. Our stop number is 2. We said the height was 1 minus f of y, or 1 minus y squared. And then our width was dy, like that. So notice that these variables are the same, as are these ones over here. This is absolutely critical. They must be the same or it doesn't work. So let's look at how to do a problem. Let's take as an example, find the area bounded by f of y and g of y when those are what's given right here. So f of y is 3 minus y squared. G of y is y plus 1. And so what we're going to do is we're going to say that our area is right here. And if we're using horizontal rectangles, then our sample rectangle is right here. It's got a width of dy, so I'm going to have the integral, something with respect to dy. And now I want to find the height, I want to find the right function, which is f of y, minus the left function, which is g of y. Notice again, this is right minus left. That's always going to be the case. Now I need to know my starting y and my stopping y, just like here. It was these y values. What you're looking for here, this is going to be the same as the variable. So my starting value, my stopping value are going to be y's because that's my variable. Just like here, my starting and my stopping values were x's because x was my variable up here. So we can find those values just by setting these equal to each other, just like we did when they were x's. So 3 minus y squared equals y plus 1. Let's get everything over onto one side of the equation. So I'm going to add y squared to both sides. I'm going to subtract 3 from both sides. If I factor that, Clearly the negative 1 is going to be down here, so I don't know what x is. I don't particularly care, but I have a negative 2 there for y and a positive 1 there for y. Putting these in is very convenient. Bottom goes on the bottom, top goes on the top, right like that. I can plug these in. 3 minus y squared minus, make sure this is in parentheses. And then, handy dandy little calculator. Whoops, that got away. There we go. We can still use finite integral for this, so math 9. Because we're using y as our variable, we're just going to put y in. So I'm going to do 3 minus, and then I can go alpha. That's this green button right there. And then y is right there above the 1. So if I hit that button, that should give me a y. Yes, it does. Squared minus in parentheses alpha 1 plus 1 close parentheses comma alpha 1. That's going to give me that y comma negative 2 comma 1. 4.5. And there we go. Let's do another example. So this is find the area bounded by f of y equals y squared and x equals 2. And I'm going to give you that graph. These ones, because they're not functions, are not ones that the graphing calculator handles terribly well. So typically you'll either be given them drawn out. Actually, I guess you'll typically just be given them drawn out. So this one is f of y equals y squared, and this is the line x equals 2. So the area bounded by is this one right here. And we're doing horizontal rectangles, so that means our width is dy. So we're going to have the integral with respect to dy, and that means this height is going to be the right function minus the left one. And we can see that what's on the right is this x equals 2, so our number is just 2. Then we're going to subtract this f of y, that y squared. Again, we need to figure out what are our starting and stopping points. We're working with y, so we need the y value to start and stop. Again, we can just set these equal to each other. We shouldn't be dealing with this x over here because we're working entirely in y, so it must be 2 equals y squared. Y would be plus or minus the square root of 2. So this one's got to be the negative 1, negative square root of 2. This one's got to be the positive 1, square root of 2. And there we are. You can just plug that in the calculator. Math 9. 2 minus alpha y squared, comma alpha y, comma root 2, whoops, negative root 2, comma root 2. There we go. Make sure with the AP test you round to 3 places after the decimal. That's just the standard. Ta-da! There are also examples that you'll see where you're given an equation that has x's in it, but you're going to use horizontal rectangles, so you have to turn them into equations that have y in it. So let's look at an example of that one. That's 2 minus x and the x-axis. So f of x is the square root of x, g of x is 2 minus x, and we've got the x-axis. So this one, if you're given it in terms of x, you ought to be able to sketch it. So f of x equaling x squared is just going to go like that. Or excuse me, square root of x. 2 minus x, that's a negative x line. It's been moved up 2. So approximately like that. And the x-axis. When we were doing this earlier, we've actually seen this problem. We saw that if we wanted to do vertical rectangles, then we had to do one integral up to here, and then another integral the rest of the way. If we're doing horizontal rectangles, though, notice that right here, the top and the bottom, or the left and the right, are touching the same things that they are all the way down here. So in this case, we only have to have one. It's just going to be in terms of dy. Now, the thing is that if we're going to have our integral in terms of dy, then we can't have these x's. I can't just do f of x minus g of x over here. It has to be y, same variable as this. So what I'm going to do is I'm going to turn these into something in terms of y. So let's see how we do that. F of x means y. So first I'm just going to replace that f of x with y. Now I'm going to get just an x over here. So I'm going to square both sides. And now, just like f of x was y, f of y is the same as x. I'm just saying that I have an equation that's going to give me some output when y is my input. So this always works. It's basically just finding the inverse function. F of x equals something in terms of x, put y in, solve for x, and put f of y in for x. We can do the same thing with this g of x equals 2 minus x. Turn that into y. Get x by itself. This divides by -1, so it's negative y plus 2. Right there. So what I can do up here is I can turn this into f of y equals y squared, and I can turn this one into g of y equals negative y plus 2. Once I've done that, I can see that the the right hand side is this g of y. The left hand one is this f of y. And now I just have to find my starting and my stopping y's. Right down here, when we're exactly on the x-axis, that's where y equals 0, right? Because we haven't gone up at all. So I can see that my bottom number here is 0, but I still have to figure out what this coordinate is up here. I can find that just by setting these equal to each other. Y squared equals negative y plus 2. Y squared equals plus y minus 2 equals 0. I'm just adding both of these or subtracting them to get them all on one side. This one we've just done. It's quite a popular one apparently. Minus 1 plus 2, y equals 1, or y equals negative 2. This is clearly a positive number, so this ending value must be 1. And there's our upper bound. Putting our equations in, g of y is negative y plus 2. F of y is y squared. That's in terms of dy. Math 9. Negative alpha y plus 2 minus alpha y squared, comma alpha y, comma 0, comma 1. 1.16 repeating. Let's do one final example and then we'll be done with all these. Find the area in the fourth quadrant. Remember, our quadrants are 1, 2, 3, and 4. Bounded by g of x equals negative x, h of x equals 1/2 x minus 3, and the x-axis. Here are axes. G of x equals negative x. We should be able to draw just looking like that. You should be really familiar with that one. H of x equals 1/2 x minus 3 has a y-intercept of negative 3 and then goes up a little bit less steeply. Okay, and we want the area between them and the x-axis. So here's our area that we're after right here. Again, this is one where we could use two different integrals going up and down, or if we draw one rectangle going this way, then it touches the same thing down here that it does up here. So this has a width of dy because it's infinitely thin in the y direction. We can see that when we start our rectangles, we're going to have a point right here. Have to figure out what that y is right there, but we can definitely see that when we stop on the x-axis, y is 0. We don't go up or down at all. So our stopping point is going to be 0. Now let's go ahead and turn these into something with y in it because we need to have a y to match this. So g of x equals negative x. Make that be y. Divide both sides by negative 1. And switch it back to our notation. I'll relabel this. G of y equals negative y. This one, h of x equals 1/2 x minus 3. Y equals 1/2 x minus 3. Y plus 3 equals 1/2 x. Multiply both sides by 2. 2y plus 6 equals x. 2y plus 6 equals h of y. My one on the right is h of y, so we're going to do h of y minus g of y. Still have to find that ending point right there, so let's come on and set these equal to each other. So this is finding bounds. Negative y equals 2y plus 6. Subtract 2y from both sides. Divide by negative 3. And that gives us our y value right there. So that's going to be our lower bound, negative 2. Oh, there we go. And when we plug that in, h of y, I'll make sure to go with the pink one, g of y, can you put that right in our calculator? Math 9, 2 alpha y plus 6 minus negative alpha y. If you want to put that in as plus y, that's totally fine. Alpha y is our variable, comma, negative 2, comma, 0. Incidentally, this is an example showing you how to do the problem. If you have a triangle, you know how to find the area of a triangle. Just find it, and that way you can check. This distance from here to here, when y is 0, 0 plus 3 is 3, 3 times 2 is 6, x equals 6. So that means that this distance from here to here is 6. This distance is 2, or negative 2. 6 times 2 divided by 2 would give us 6. If we're looking at the signed area, this is a negative area. If we're just looking at the overall area in a sense of how much stuff is there, geometrically speaking, then we would get the positive 6. So the positive 6 is okay here. When we're doing these types of area and volume problems, we're ending up with a positive area regardless. It's when we're doing the sort of change in interpretation that it's really important to have the negatives and the positives. Okay, this concludes the notes for Geometric Applications 3.